Okay, what observation is the basis for Ohm's law? V equals IR. So current depends on resistance and potential difference. Current depends. So let me go through the ones I don't think are correct. Current is unrelated to resistance. So current is the I and there's the R. They're obviously related. So that one's out. That's a no. The higher the current, the higher the resistance. So when you look at an equation like this, what they're trying to show you is that if one goes up, like in this case, they're saying I goes up. Well, for V to stay the same, like imagine V is a number. If this number goes up, then R has to go down, but it says they both go up. So that's a no. And the current depends only on the conductor's resistance. That's not true. It depends on voltage as well. So I would tend to think that this is the best choice there for that one.
Okay.
All right, next one here. And again, use all the available resources that you have to answer these questions. The difference in energy carried by electrons at different points in a circuit will determine the. So I want to say it's voltage, but I want to just double check that before I mean, this is just a definition. Yes, this is just a straight definition of voltage. There's nothing more to that. Let's go. So sometimes when you're studying this, I'll add this here. They use a reference to water, like water flowing in a stream, and the voltage is like how much water passes through one point compared to another. They use some analogies like that may or may not be helpful. Okay, so let's go to number 3. Number 3 will be easier answered with Ohm's law again. Okay, according to Ohm's law, V equals IR. If the current through the load increases, so if I increases, what happened to the voltage across it? So if the resistance is the same, which I guess we're supposed to assume it, we think that it does increase as well. It's like if one side of the equation goes up, then the other side must also increase. And for a given load, I think is referring to a constant resistance.
Okay.
So I would tend to think it increases here. Let me just quickly check and see if I can confirm that. But it all comes from this equation, the Ohm's law equation. Yeah, I guess that would be my best answer on that one for you.
Okay.
Okay, next question. In which circuit will the bulb or bulbs grow the brightest? So this question is based on like understanding how voltage and resistance and current all connect to a bulb.
Mm-hmm.
So we know that a bulb with a higher wattage which we go to the store. Higher wattage means it's brighter. Wattage, it refers to power. Power is, what is power? I squared V. I can't, I'd have to look that up, but it's related to current and voltage. So maybe there's a picture of this that I can find. Are these all in series? Looks like circuit with 2 bulbs in series and 1 battery. Just give me a moment here to find a reference. So, okay, let's diagram them. 2 bulbs in series with 1 battery. So battery is your voltage source. And you can think of your bulb as a resistor, but it's a bulb. I guess that's the bulb. Well, that's really not drawn well. And then there's another bulb here.
Okay.
And so the bulbs share the voltage source. So that's a problem. Okay. And that's why I asked if they're in series, because that really doesn't matter. If they're in parallel, they share it, but they don't take away from each other. So that's number one. Number two is 2 batteries. So like 2 voltage sources, basically double your voltage source. But there's only one bulb this time. Okay. And what that does is it means it has more voltage for the 1 bulb. That's good. That's better. And so there's 1 bulb. The third one, that's number 3, would be one bulb and 1 battery. So 1 voltage source, and they're all voltage sources the same, except this one's double. And 1 battery. Okay. So this one, it gets all the bulb gets all the voltage source, doesn't have to share it. Okay. But this one's got twice as much. So the answer is 1 bulb with 2 batteries, because it's much larger.
Okay.
Okay, so we got some numerical questions coming up. Those should go a little better. Sometimes the qualitative ones are a little harder for me, because I'm not as much of an expert as this, as say other things. But it's all Ohm's law, as we're doing V equals IR here. So this is a pure Ohm's law problem. It says an electric appliance draws 1.5 amperes. So that's your I. When it's connected to a 24-volt source, and they want you to solve for R. And it's kind of an oversimplification of Ohm's law, but it does work.
Okay.
So 24 divided by 1.5. Let's get that number. Got a 16 ohms. That's purely Ohm's law.
Okay.
Okay, so number 6 is asking about equivalent resistance in each of the circuits. So when they're in parallel like this, when they branch, this is called a branch. When they branch, the total resistance is 1 over the individual ones like this. So 1 over the total that you want is 1 over 1 plus 1 over 2.
Okay.
And so this is 3 halves. And so you flip the number on the right when you have a reciprocal on the left. So that's 2/3. And the thing is that's important here to remember is that and when they're in parallel, parallel is always less than series, and unless except for some weird scenarios. So that the total resistance is always going to be less in a parallel. So like when you're looking at the second option, which I mean we can do real quick. It doesn't take that long, but you'll see that the total resistance in the second circuit or second resistor sequence is our total is 2 plus 3 or 5. So see how it gets bigger, like it combines. So like we don't need to do the fourth one because it's going to be the fourth one is a 1 ohm and a 2 ohm resistor. They're just going to add together, but we do need to do the third one. So 1 over the resistance total here is 1 over 2 plus 1 over 3. And so our formula here, you can either add up the right-hand sides, which is usually a good idea here. This becomes 5/6. So the flip of it is 6 over 5. And notice that that's bigger than the 2/3 that we got in part A. So part A is the smaller one. This would be your best answer. Is that okay?
Yeah.
Okay, so the next question here is 7. Total resistance. Okay. So this one maybe appears complicated. It's a circuit that's, let me snip it in here. It's a circuit that's in series because there's no branches. It's just the one loop. So the total resistance, you just add up the 2 resistors, the 10 ohm and the 90 ohm. And sometimes you can just look at the units and just, oh yeah, they're both resistors. So I'll just add them up, 100 ohms.
Okay.
So there's some extra information there that, Okay, so we're going to do 8 next. The equivalent resistance of 2 ohm, 3 ohm, 5 ohm, 6 ohm resistors connected in parallel. So parallel is that key word. When they're parallel, it's 1 over RT. Is that 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. So it's 1/2 plus 1/3 plus 1/5 plus 1/6. So probably a good idea to add these up on the right there. Do that real quick here. So that is 6/5. And then you flip the left, you flip the right. So the total resistance is 5/6, which, well, let me go see what, I'm going to go to a different email, but I think you're looking at 0.87 ohms. Oh, 0.83 ohms.
Okay.
So it's all about knowing whether the fact that it's resistors, because your next section will be capacitors. It may be, I don't know what your course is going to go, but capacitors are in series and parallel again as well.
Yeah.
Okay. All right. So sorry, I didn't even grab the question. It says the current is greatest through which of the light bulbs. So there's like, think of current as like the flow of water. So the flow of water here, it has to split at these two places. Like imagine a water runoff. You can think of current as water. It has to split here. So the current through 1 is the same as the current through 2 and 3, but then they join back up.
Mm-hmm.
And so the current is greatest when it's like it's not being split up, I guess is the point. Because when you get back to this point in the circuit down here, they've joined forces again.
Oh, okay.
Yeah, that's sort of a simplistic way of doing it. Now, the more mathematical way to do it is actually like assign values and go through the calculations, but that's my best sort of explanation of it. They could also ask where it's the least, and it's the least where it's being split. At a point like here, split between those.
Mm-hmm.
Excuse me. All right, so that let's go to the next one. Oh boy. So the next one asks about removing a bulb, and this is where if I were more of an expert, I would understand what the intent of this question is. If they mean like it's literally the circuit is broken, or there's just, it's not there. So if this isn't here, this bulb 1 is removed, you effectively have just a circuit that looks like this, where you got 2 bulbs, and then you got this other bulb down here. Okay.
Mm-hmm.
But now we got to go figure out like which response is that one. Oh, okay. So there. So when you remove this, the current, I think, still flows to it. Okay.
Mm-hmm.
But there's just well, I take that back. So if this is removed, see, one of the options is all of the bulbs go out, and that's where I don't think that's the answer, but let me just check here.
Okay.
This is so much easier done when you have a circuit, or little breadboard thing to like see it. Maybe you've got a lab that goes along with this class, or will at some point.
Mm-hmm. Yeah, we're not really given a lot of like visuals, so I feel like that's why it's difficult. It's mostly just like a presentation and you click through it.
Yeah. Yeah, you really need a video of like this circuit, and then you'd say, oh yeah, you pull it out, and then you would know, oh, those get brighter, or they get So we said before that 4 was the brightest, that these were less bright. And so if you can visualize it being like this circuit on the right here, the current flow is the same through all of them,
Mm-hmm.
which means that the brightness will be the same. So if you had to, if you're sort of asking me, what's the best choice here, it's that when you remove it, because these are, let me grab these, because this is in parallel, the fact that this is broken here, there's still going to be current routed out to the right, and it comes back. So it does,
Mm-hmm.
they don't go off. But what does happen is that it turns into the circuit on the right, and they all have the same. There is now a series circuit, and they're all of equal brightness. I guess would be my best response for that. The visual, I don't have like a Desmos for circuits where we could just do this real quick, and that would be the ideal way to do this question.
Yeah.
So that's where that's where Paul may be a little bit better help here, but understand if you don't want to do that, I'll keep helping you. This isn't all that impossible. Nothing's impossible here. So
Yeah.
like this next question is very straightforward. Okay. It wants the current flowing through the circuit. And that's a V equals IR problem. But you have to first like turn this parallel into a total. You need to know what the total resistance is of the circuit. So we've done that a few times. 1 over RT is 1 over 2 plus 1 over 6.
Mm-hmm.
So what is that? 2/3. So I think it's 3/2 is the, yeah, so this is 2/3. So you flip it, 3/2. So that's 1.5 ohms. So that's the total resistance in the circuit. That's this R up here. And they give you your voltage. So you're going back to this equation, you're going back to Ohm's law. And you're looking at 10 equals I times 1.5, divide both sides by 1.5, and you get well, let's see here, 6.7 amps. Some weird rounding in this.
Okay.
Okay, so it looks like the next few questions are getting a little more involved here. We'll do our best. These are definitely overwhelming the first time you see them.
Yeah.
Okay, determine the current at point A in this circuit. Okay. So let's look here, some of our options. So one thing we could do is V equals IR, but we don't know the voltage across this. So if we knew the voltage across this resistor right here, which you might think, oh, it's 110 volts, but that's shared throughout this. So what I perceive that you have to do here is you have to come up with the equivalent. So let me make another point here. We're talking this for like the current in A, it branches to B and C, and then they come back together down here. So if we just find, so the current at A is actually the same as over here. So because the current's constant in the circuit. So if we find the total resistance in the circuit, okay, which we can do, we can then use Ohm's law to find the current because we've got the voltage source. So that's where you convert this one's in this first resistor, and then you have these two. These are in parallel. So we want to find the total resistance in these two on the right. So what that will do is we'll have a circuit that now looks like this. Okay, so this one's still 10 ohm, this one's still 15 ohm, but we've got to figure out the equivalent resistance of these two. So that's where you're doing the 1 over RT equals 1 over 40 plus 1 over 30. So see if you can solve that for RT. I'll be right back with you in a moment.
Okay.
Okay, so you can first add them up, 1 over 40 plus 1 over 30. It's okay if you want to do decimals, but just keep in mind that you can also do fractions. So then you flip it, so your RT is 120 over 7, or if you're doing that with a calculator, you might get 17.1. Okay, so that's this one here, 17.1 ohms. So now when they're in series means there's no branches, like extra loops is what those are called. You've got 10 plus 17 plus 15. So your total resistance in the circuit, not just this part of the circuit, but the whole circuit is 10 plus 17.1 plus 15. Okay, so that's it's 42.1 ohms. Okay. And it feels like a lot of work, but we're almost there. So we go back to our V equals IR. Okay. Your voltage at the source is 110. Your current is what we're trying to find, but the resistance is 42.1. So we solve for I by dividing both sides by 42.1. So that's 2.6 amps.
Okay.
A lot there.
Yeah.
Okay, looks like we're up to a new email. Maybe. Are we up to 13 or 14? What are we up to?
We are up to question 13.
13. Why don't I say 13? I'm just going to grab this one because it's actually not too bad.
Okay.
And then I'll go look for 13.
I think 13 might be the one that's in an email by itself, I think.
Okay. I'll go back to that. So here, this looks like it might be the one after 13. When connected to a 12-volt battery, so that's your source. The current in a headlight, so you treat the headlight as like a bulb. Bulb here. Okay. So they're saying 12 volts, the current's 4 amps. What is the resistance? That's a V equals IR problem. So your voltage is 12, your current is 4, and you have to solve for R. So R is 3 ohms.
Okay.
So I'm looking at 13. I should know this, but there's there's some relationship between the components in the circuit. Let me snip it in. And the number of ammeters and voltmeters. So if you own a car, I don't remember if you're driving, but your car has a battery, positive terminal and a negative terminal. If you were to hook up a voltmeter to it, which is maybe a better reference, you have two wires coming out of your voltmeter. One goes to the positive and one goes to the negative. Okay. Because with a voltmeter, you're always measuring it across a thing. Like you're always breaking it in. You're going to like point A and then point, well, this is a better example, A and then point B. So when they tell you the voltage of the source is 110 volts, they're saying when you put a voltmeter there, you get 110 volts.
Okay.
So in terms of how many voltmeters would the student need? So since they might want to measure the potential difference across the lamp, electromotive force of the cell. Okay. Like you'd want to be able to put something at C and D and maybe like E and F to get the voltage across each of those points. Now the current in the circuit you get with an ammeter, and the current is the same because it's a series circuit. The current is the same throughout. So you only need one ammeter. And I guess that's why I'm leaning towards the answer of 1 ammeter and 2 voltmeters.
Okay.
But in full disclosure, like you would just move your voltmeter and you would move your ammeter. But I think they're saying like if you want to measure them all, if you want to have like everything connected at one time.
Okay.
So let's another way to look at it is for current you need an ammeter. Current you need an ammeter. For potential difference, you need a voltmeter. And for the electromotive force of the cell, let me just double check that. So electromotive force is a volt. So this is also a voltmeter. So yeah, that seems to be consistent with what we just said. So it's almost as much about the words as it is the circuit to be able to do this.
Okay.
Okay, so the next question here, I think is 15, where it says a device is added to a circuit. Does that look right to you?
A device is added to the circuit.
And they're asking which of the following symbols should be included?
Yes, this is number 15.
Okay. So some of it's cut off for me, but it's basically asking you for the symbol of a current or an ammeter. So it's the universal symbol for an ammeter, which I don't even know what it is. Oh, it's an A. So is there one of those?
Yeah.
Okay, that would be the one because that's total current. Current is an ammeter.
Okay.
All right, so 16. I'm not seeing 16. Could you maybe
16 is the following circuit diagram is partially incomplete. A device is added to the electrical circuit to vary the current in lamp 2 only.
okay, so to vary the current. Okay, so that's a is that a potentiometer? Okay, so device to vary current. A rheostat, sorry. So we're looking for a rheostat, and then we need the symbol for that. And let's see if we can find the universal symbol for a rheostat. Okay, so rheostat is this one. It's probably, there's two. So here's one, it's got the arrow. Is that one of the options?
Yes.
Okay. Great. Right, I'm gonna skip 18, but because it's just for time, make sure I get 19 and 20 in, because I know that we can do these real quick. Okay, 5 ohm, blah blah. Okay, so they're connected in series. So when they're connected in series, you add the resistors. So it's 5 plus 10 plus 12 plus 16. I think we already did one like this. So what's that? 43 ohms. And then they want the current. That's V equals IR. I is voltage divided by resistance. 120 volts divided by 43 ohms. I believe it's 2.8 amps on that one.
Okay.
I think we already did one just like that. Same numbers. Great reason to keep your old quizzes, print them out as PDFs. That way they're searchable, things like that. So 5 resistors are connected in parallel. So we've actually already done this one a bunch of times. 1 over R total, because they're in parallel, it's 1 over 10 plus 1 over 10 plus 1 over 10 plus 1 over 10 plus 1 over 10. So that ends up being 1/2. And RT ends up being 2 ohms, like we saw. And we did a problem just like this in our previous lesson today.
Okay.
Okay, so let's go to the last question here. Okay, a circuit contains an electrical power supply, a lamp, which is a bulb, an ammeter, so that's to measure current, and a variable resistor. The resistance of the variable resistor is increased. What happens to the brightness of the lamp? Okay, so let me try to show this. So we have a voltage source, and then we have a bulb. And then we have this variable resistor. Oh, I guess they use that for variable resistor. Okay, so the current is always the same. Okay, but when you increase the resistance, right, the total resistance increases. So V equals IR. R really is, in this case, it's the resistance of the bulb plus the resistance of the resistor.
Mm-hmm.
So if that one goes up, that also goes up, and then the current. So think of it this way. Let's just say this was, let's make nice numbers here. So we start out, it's 120 equals I times R. Okay, and let's make R 10. Okay, in this first scenario. So then I is 12 amps. Okay, but then this goes up, like we increase the resistance to 20. Well, so now I is, it's now 6 amps. So the ammeter decreases. The current decreases. So when you increase resistance, the ammeter decreases. So that gets us down to those two options.
Okay.
And brightness is based on power, and power is based on current. So if the current goes down, the brightness also goes down. So this would be my best option. Again, this is best seen like in an actual circuit in like a lab, if that were an option. We're here. All right, did we get through everything?
Yes, I think so.
Fantastic. Okay, I will send out the notes for both of these lessons here on the next few minutes. And thanks for letting me reschedule with you. Couldn't tell, definitely not feeling great, but glad to help.
Yeah.
And I'll be ready to go on Monday to keep going, helping you.
Okay, thank you for squeezing me in, even though you didn't feel well.
Of course, you're a great customer. And I'm glad you're doing stuff over the summer. I'll see you next time.
Yeah, bye. Thank you.